So we have our review question. Which of the following sums represents approximating the area under the curve y equals x cubed from x equals 0 to x equals 10 using a Riemann sum with n equals 100 equal subdivisions and right endpoints? All right. Well, one of 5 options. A, B, C, D, or E. Does anybody have an answer? Sorry, what? D? D is right. All right, now there's a couple of things to note. We have a generic formula. So B minus A over N, where does the B minus A over N come from? Do we remember what this represents? So B minus A, so we're going from A to B. So those are our interval points. So B minus A is what? Well, it's like the distance horizontally between the start and stop. What does B minus A divide by N? So N is the number of subdivisions, so what does B minus A divide by N represent? So think about what Riemann sums are. Riemann sums are areas of rectangles, so these are your widths. So if you're going to do your Riemann sums, you want to make sure you have your widths about you, right? Okay, all right. What else do you need in addition to your widths? The heights. The heights come from the function. So that's why we're adding up. So essentially it's a width times a height, but since the widths are always the same, you can pull the width out. So the way you get your heights is you plug things into your function. So here, these are your heights. Your widths are always the same if you're equally spaced. Your heights vary depending on the function. And we say, okay, well, how do you get the heights? Well, you plug points into your function. You're starting at A, and then you say, well, I'm going to move over, B minus A over N is your width. I'm going to move that many steps over, and that'll get me to the right endpoint. Not the wrong endpoint, the right one. And plug it in. So this is the generic formula. All right, well, we know in our case A and B are 0 to 10 and N equals 100. So 10 minus 0 over 100 gives us 1 over 10. And then we have 100 subdivisions. So our sum goes from 1 to 100. And just knowing that the sum goes from 1 to 100, that's enough to rule out A and E automatically. Because there's just not enough terms in your sum. Because you need to have 100 terms. And then we say, okay, A plus B minus A over N times K, well, that becomes K over 10. Well, now we say, but our function we know is a very particular function. It's x cubed. So it's K over 10 cubed. And that helps us say, aha, in our last one, we're going to have a K over 10 cubed. And so we see that exactly matches D. All right. Well, good. Good. Any questions? If you're like, oh, man, I really want to do a lot of Riemann sums, have I got good news about today? We're going to do a lot of Riemann sums today. It's our grand farewell party. All right. Well, the quote for today, Arthur Ashe, famous tennis player. Start where you are. Use what you have. Do what you can. I think a lot of times in life, and I know I speak for myself, and may or may not apply to you, I sometimes feel like I have to wait for something. It's like, as soon as a certain event occurs, maybe like daylight savings, then I can start doing activity X. Or once the exam is less than 24 hours away, then I can start studying. No. Don't wait. Start now, wherever you are. And you might say, but I need to wait until I have all the tools. Use what you have. Do what you can. And the sooner you start, the better off you are. Don't procrastinate. It's like, I don't know if anybody experienced it, but there was issues with the homework system last night where it stopped working for a little while. And pro tip, it turns out that the due date is not the same as the start date. So you are allowed to start your homework before the day it's due. So for instance, if it's due on a Sunday, you can start like on a Wednesday. Wow, it's a crazy idea, but crazy enough, it just might work. All right. So, quick recap. We have some sum properties, and you don't need to remember too much other than at some point I'm going to come and grab these pieces here. So this was from last time, and this is just literally copied from last time. So we did this last time, and I want to note that there. Also from last time is we said, how do we find area? Well, again, we have our generic formula, our b minus a over n, our f of a plus k times b minus a over n, our width, our height, add them up, and that's if we split into n, but of course, for better results, choose a bigger n. Let n go to infinity. It's hard to be bigger than infinity. And I know what you're thinking, what about infinity plus 1? That's still infinity. So I know how to win against my toddlers. You know, I can do that. All right. So we'll have that for reference as well. So let's find some areas. We'll start with the function 1. Find the area under the function f of x equals 1 between 0 and b, and we're going to do it in two ways. Geometrically and using a Riemann sum. Okay, so let's think geometrically. What does the function f of x equal 1 look like? Yes, a line. It's not even just a line, it's a flat line, which is always 1. And we're going from 0, 0 to b. So we're trying to find this area. Okay. How do you find this area? What kind of shape do we have? It's a rectangle. What are our dimensions? 1 by b. So geometrically, rectangle, and we have a 1 by b, so that says area is b. Nice. We're doing calculus. Okay. Well, now let's do it the other way. Okay, using a Riemann sum. So, I'm going to write down the generic formula. We have limit n goes to infinity, b minus a over n, and sum k equals 1 to n of f of a plus b minus a over n times k. Okay, now, since this is our first time writing this formula down, I'm just going to make a quick note. Since a equals 0, this simplifies. So this becomes the limit as n goes to infinity of b over n times the sum k equals 1 to n of f of b times k over n. So this uses, just plug in a equals 0. Okay, so let's compute this sum. In our case, what's our function? 1. So this becomes the limit as n goes to infinity of b over n times the sum k equals 1 to n of 1. Now, what is the sum from 1 to n of 1? And in case you're trying to remember, what is that sum? It's 1 plus 1 plus 1 plus 1 plus 1, and you keep adding 1. What do you get if you add 1 a bunch of times? Well, but we're not going to add 1 infinitely many times. How many times are we going to add 1? We're going to add 1 n times, because we start at 1 and we go to n. So this is n. So this is the limit as n goes to infinity of b over n times n. Now, true story, the n's cancel. Oh, nice! So it's our limit as n goes to infinity of b. And what happens to b as n goes to infinity? Nothing. It stays as b. Nothing happens to it. And so we say, aha, the area equals b. See? We got the same answer. Isn't that nice? All right, so we've done it geometrically and we did it using a Riemann sum. All right, I'm going to add this to our chart here. And you might say, what chart? The chart you haven't seen yet. Our function f of x was 1. The area under f of x between 0 and b was b. Okay, we're going to add to this chart. Our goal is to fill up this chart today. Okay, next function. Find the area under f of x equals x, where x goes from 0 to b, geometrically and using a Riemann sum. Okay, cool. So let's sketch this function. F of x equals x looks like a line. We're going to b. So we're after that triangle. Okay, so we're after the area of a triangle. How do you find the area of a triangle, thinking geometrically? Base times height divided by 2. Cool. What's the base? It's all about the base, about the base. What's the height? It's all about the height, about the height. What is it? B, right? Because at this point, f of x equals x. So if I'm at b, the height is b. So geometrically, the area, 1/2 base height, 1/2 b squared. Okay, cool. Now, let's do it another way. Using a Riemann sum. Okay, so limit as n goes to infinity of b over n, sum k equals 1 to n, f of b times k over n. This is just, I'm using the special case for a equals 0. Now, our function f of x is x. So this is the limit as n goes to infinity of b over n, sum k equals 1 to n, of b times k over n. Wherever you plug into your function, that's what comes out. F of x equals x. Now, notice here this sum talks about k. So anything which doesn't have a k, I can treat like a constant. So I can pull out the b, because that doesn't depend on k, and I can pull out the n. So this is the limit as n goes to infinity of b squared over n squared times the sum k equals 1 to n of k. Do we know how to add that sum? Did we talk about this sum? I'm willing to accept a yes, no.
Yes.
Yes. It's this one. It's the one with the dots. So the sum from 1 to n of k is n times n plus 1 over 2. Okay, so this becomes the limit as n goes to infinity of b squared over n squared times n plus 1 over 2. And if you think about what this says, this is limit as n goes to infinity. I'll put the b squared over 2 in the front. And then I'm going to take the n squared and just divide it into the terms. So think of it at the end distributing here. So you have n times n is n squared. Divide by n squared, 1. N times 1 is n. Divide by n squared is 1 over n. All right. Now, question. As n goes to infinity, what happens? It's a little bit harder than last time because there's actually an n showing up here. What happens as n goes to infinity? This has to go to 0, and it approaches b squared over 2. Now, were we expecting it to be b squared over 2? Yeah, because we already knew the answer. If these didn't match, we'd be nervous. And at this point, you're like, why do we do Riemann sums? Isn't geometry better? When we can. It turns out there's not very many shapes we're good at in geometry. What are some shapes we're good at? Rectangles, we've already done that one. And triangles, we've already done that one. We're running out of shapes we're good at. Okay, so if our function is x, the area was 1/2 b squared. Okay? So we've expanded. Not too many slots left. All right, are we ready for our next one? No. No. We're going parabola. Find the area under f of x equals x squared. X goes from 0 to b, and we're only using Riemann sums. Now, why only Riemann sums? Because we don't have a slick formula for this shape. So we don't have something to fall back on. Okay, so we have our x squared, and we're going from 0 to b. So there's our shape. All right. Well, what do we do? We use a Riemann sum, right? Because it tells us to use the Riemann sum. So, no surprises. Okay. So, we're going to take a limit. N goes to infinity of b over n, sum k equals 1 to n of f b times k over n. So, that's just definition of Riemann sum for an interval from 0 to b. No surprises on that part. That becomes the limit as n goes to infinity of b over n, sum k equals 1 to n. And here the function says whatever you put in it, you square it. Okay. Well, we'll do the same thing we did last time. We'll pull out anything that doesn't depend on k. What doesn't depend on our k in our sum? We have the b squared, because that's squared. So we're going to get a b cubed. There's an n squared down, that comes out. That's an n cubed. And then we have the sum, k equals 1 to n of k squared. All right. Do we have a formula for the sum k equals 1 to n of k squared? Yes. That formula. So the sum k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 over 6. All right. So for now, we'll just take it as is. So we're going to copy that. So this is our limit as n goes to infinity of our b cubed over n cubed. Then this becomes n times n plus 1 times 2n plus 1 all over 6. Now, if you multiply that out upstairs, and who doesn't like multiplying out polynomials? It's a great pastime. We have our b cubed over 6n cubed times 2n cubed plus 3n squared plus n. That's what it turns out to be. But what can we do? We can take this n cubed and distribute it in. So this becomes the limit as n goes to infinity of the b cubed over 6 in the front. Then we have 2n cubed divided by n cubed, also known as 2. 3n squared divided by n cubed, 3 over n. N divided by n cubed, 1 over n squared. What happens when we let n go to infinity? The 3 over n and the 1 over n squared do what? Go to 0. So what's left? b cubed over 6 times 2, 1/3 b cubed. All right. Now, there is a punchline coming up at the end of today. If you're looking at this and saying, oh my gosh, this seems like a terrible way to find area. We were going to see a punchline at the end of the day like, oh, that's so much better. Why did you make us sit through this? But you have to appreciate it. Okay, so how are we doing? So far, so good? You're probably thinking, I don't want any more polynomials. Don't worry, we'll switch it up. We know you want something new. Okay, so x squared became 1/3 b cubed. All right. Well, time for everybody's favorite function. Any guesses? Oh, that's not everybody's favorite function. That's just mine. E to the x. Classic. Classic. This is going to be good. This is going to be fun. Okay, so let's remind ourselves what e to the x looks like. We have this exponential function, f of x equals e to the x. So we're going from 0 to b. All right. It's not so obvious. Of course, even the parabola was not so obvious. But let's see if we can't figure this out. Okay, well, I think we should use a Riemann sum. And the reason I think we should do that is it says, use a Riemann sum. It's a pretty strong hint. Very, very strong hint. All right, well, so limit n goes to infinity of b divided by n, sum k equals 1 to n, f of b times k over n. Definition. Okay, so what do? Well, this is b over n times the sum k equals 1 to n, and it's e to the power of bk divided by n. Now it's a little bit trickier, like what's going on here? What's going on? And we want to think about it in terms of k. K is really what's driving the sum. It's our index. So I'm thinking, okay, I'd like to make sure I have this expressed neatly in terms of K. So I'm going to use a fancy trick. And I'll write it down for reference. If I take e to the power s and raise it to the t, what does that equal? E to the s times t. So what we can do is we can say, oh, if you have multiplication, you can actually pull things out and think of it as a power. So this is limit as n goes to infinity, b over n, sum k equals 1 to n of e to the b over n to the power k. Now, that might not seem to be an improvement, but it actually is an improvement. Because if for a moment we were to call this part here as r, then we have the sum, k equals 1 to n, of r to the power k. Why is that useful? Ah, he grabbed the sheet. It's useful because we know how to sum that. We can get rid of the sum. So if I have sum of r to a power k, it's r to the power n plus 1 minus r over r minus 1. All right, so using that rule, and I'll write it down here. This is r to the power n plus 1 minus 1 divided by r minus 1. Then we get the following. This becomes our limit as n goes to infinity of b over n. This, oh, there's no more sum. I was so excited about writing sums. Times e to the b over n minus 1, e to the b over n to the power n plus 1 minus 1. That's just a big time symbol. All right. Cool. Nice. Nice. Well, we can write this as the limit as n goes to infinity. And I'm going to think of this as a b over n upstairs times. Now here I'm going to write this as e to the b over n to the nth power times e to the b over n, just to the first power. So this is the n plus 1, just breaking it up into two pieces, minus 1 over e to the b over n minus 1. All right, I think I've accounted for everything there. So, cool. What goes on? Is there another name for e to the b over n to the nth power? E to the b. Okay, so this is our limit as n goes to infinity of b over n times e to the b times e to the b over n minus 1 over e to the b over n minus 1. Now, right now, it maybe isn't so clear what's going on. Notice how everything involving n is really a b over n. So let's change our names. Changing names, it's a really cool thing in math. It's how a lot of math gets done. So let's introduce a new variable. We're going to call it b over n. What do you want to call this new variable? What?
Make it S.
We can make it s, sure. S b over n. So, limit as n goes to infinity of, oh wait. What happens as n goes to infinity? What does s do? S goes to 0. Of s times e to the b, e to the s minus 1 over e to the s minus 1. Let's find this limit. So, when in doubt, when you're finding a limit, what do? Plug it in. When you plug in 0, what do you get upstairs? 0. When you plug in 0, what do you get downstairs? 0, which means more work. More work. And people are like, oh, that's why Steve was so excited. All right, what's the more work? L'Hopital, mon ami. Yes. We can pull out L'Hopital's rule. Okay, so here we go. We're going to L'Hopital this problem. So this is the limit as s goes to 0 of, we'll start with the downstairs. What's the derivative of e to the s minus 1 with respect to s? E to the s. What about upstairs? Well, got to do a product rule. The derivative of the firsts will be 1. So that leaves you e to the b, e to the s minus 1 plus s. What's the derivative of, well, e to the b is a constant. Derivative of e to the s? E to the s, and the derivative of minus 1 is 0. Okay, now what happens when you plug in 0? It's not any more work. The end is in sight. Downstairs, e to 0 is 1. E to 0 is 1, so you get e to the b minus 1. What about this last part? You get 0, because s is 0. So our final answer for the area is e to the b minus 1. That's kind of nice. That's going to make our chart. So when the function was e to the x, the area was e to the b minus 1. All right. See how our chart's filling up? We only have one more slot left, which is good because we don't have infinitely much time left. All right. Any questions? You hanging in there? We have one more to go. All right. Our last area problem.
They do have plans for people
Find the area under the curve square root of 1 minus x squared. And we're going from 0 to b, but b can't be arbitrarily large. We have to stop at 1. And we're not going to do any Riemann sums. And I know how you're feeling like, oh, I was getting so good at Riemann sums. I know, I feel your pain. But that being said, it's hard to do these Riemann sums. Okay, so we're going to do it geometrically. So, do you recognize this curve? F of x equals the square root of 1 minus x squared. It's what? It seems familiar.
Arctan.
What is it?
It's the bottom of the arctan.
It's not arctan. Square root of 1 minus x squared. What does that look like? Sorry, what? Ooh. You're looking ahead in the future. Arcsine is in our future, spoiler alerts, but it's not the arcsine function. Just what does the function y equals square root of 1 minus x squared look like? What? Oh, okay. Normally I'd give this away, but this is one I really want you to know. So we're going to drive it home. If you can't guess the shape, give me a letter.
A. Oh, no.
Now, is O a guess, or it's like O, that, I thought it was going to be an A? C.
Cosine.
It's a circle. Oh. Right? Y equals square root of 1 minus x squared. Square both sides. Y squared equals 1 minus x squared. Move the x squared across. X squared plus y squared equals 1. It's a circle of radius 1, aka the unit circle. Not just any circle, it's the unit circle. The one that you spent a whole course on in trigonometry, like, I will learn these points, and I will never forget these points. And so, 1, circle. So let's pretend I can draw a circle. All right, so we're going over to distance B. That's the area we're trying to compute. Now, I don't want to shade it just yet. Not so clear how to find that area. So I'm going to do something a little bit suspicious. I'm going to cut it into two pieces. So that there's a piece above, aka the pizza slice, and there's a piece below, aka the triangle. All right. If we can find those two areas individually, their powers combined, they will give us the area. Which one do you want to think about first? Triangle. Okay. We're cool with that. Notice that this point is on the circle. So that says if my x value is b, my y value is the square root of 1 minus b squared. Which means if the base is b, this height is what? Square root 1 minus b squared. So we have our two pieces. So our area is, we'll say this is our triangle. This is our wedge. So 1/2 b square root 1 minus b squared. Okay. Well, that wasn't so bad. What's left?
Pizza slice.
We got the pizza slice. Yeah. All right. So, for that, some quick geometry recall. Imagine you have a circle. Not too hard to imagine in this problem. And imagine you have a slice. Again, not too hard. And imagine you have the angle of that slice. And you want to know the question, if I know that angle, can you tell me how much area is in that slice? Well, the observation is to say, if you take the angle, divide by going all the way around, that's the fraction of the circle that you have. So that's the same as the fraction of the area there is in a whole circle. So if you move the pi r squared across, you get that area is equal to 1/2 r squared theta. Now in our case, what is our radius? Radius is 1. So if we could just figure out this angle and take half of that, we're done.
Half of that angle?
Because there's a 1/2. So half that angle. Now that angle being, it has to be radians. Because this 2 pi is radians. All right, so now we start thinking about cool. And we start thinking about how can we get that angle? Well, that angle is the same as this angle. These two angles match. And we have a triangle here. And it's not just any triangle. It's a triangle with a hypotenuse of 1. Yes? So let me ask you a question. Of these three sides, which side do you not want to use? We don't want to use that one. So let's use the opposite and the hypotenuse. What's the trig function that relates opposite and hypotenuse? SOHCAHTOA this, come on. Sine. Sine of theta is b over 1. Now, we don't want sine of theta, we want theta. How do we get the theta out of the sine? Sine inverse, the arc sine. So theta is arc sine b. We already figured out if we could just find the angle, we just need to times it by a half. So the area of the wedge is 1/2 arc sine b. And that's the answer. Just like you thought, right? Cool? Okay, so update our chart. F of x square root of 1 minus x squared. Area under f of x, we're just going to copy that down, 1/2 arc sine of b plus 1/2 b square root 1 minus b squared. That's why we needed space. All right. Now, you might be looking at this and saying, there's some space on this page, Steve. Why don't we make this chart bigger? You're right. We should add a column. All right. We're going to take the derivative of the area with respect to b. So here's b. The derivative of b with respect to b is 1. Yes? Don't look here. Just look here. Derivative of b with respect to b, 1. What's the derivative of 1/2 times b squared with respect to b? b. What's the derivative of 1/3 b cubed with respect to b? b squared, right? Because it's going to be 1/3 times 3b squared. What's the derivative of e to the b minus 1 with respect to b? What about the minus 1? It's gone. Constant. What's the derivative of 1/2 arc sine of b plus 1/2 times b times square root of 1 minus b squared? Let's do the work. Okay. Derivative of arc sine, anybody remember that? 1 over square root 1 minus b squared. That's the derivative of arc sine. Good times. Next we do the product rule. We have 1/2 times derivative of b, which is 1, times square root of 1 minus b squared, plus 1/2 times b times, now for this one, it's going to be a 1/2, 1 minus b squared to the minus 1/2 times minus 2b by the chain rule. Okay? So far, so good. Now, some nice things happen. I know you're thinking like, I bet you I know what we're going to end up with. I bet you do. But it won't seem magical if we don't work for it. All right. So, what do we have? Well, everything has a half. So I'm going to pull the half out. Everything has a square root of 1 minus b squared. Let's pull out 1 minus b squared, but which power should we pull out? 1 minus b squared to what power? -1/2. Because that's the lowest power. What's left from the first term? 1. What's left from the second term? It will be, we got the half. Did we get the square root of 1 minus b squared? We factored out 1 minus b squared to the minus a half. What power of 1 minus b squared is left? 1 minus b squared to the 1. 1 half subtract minus a half. What's left here? So we got the half pulled out. We got the 1 minus b squared to the minus a half pulled out. What haven't we pulled out? We haven't pulled out the minus, and we haven't pulled out that b or that b. So b squared. So this is 1 half, 1 minus b squared to the minus a half. Now, what do you get when you put these together? 2 times 1 minus b squared, yes? 2 times a half cancels. 1 minus b squared to the minus a half times 1 minus b squared gives us 1 minus b squared to the positive half, or the square root 1 minus b squared. Who could have seen that coming? Probably everybody who said, "Don't do it, Steve, don't start." Now, you might be wondering, why did Steve cover up that first column? Look at these. 1 versus 1, x versus b, x squared versus b squared, e to the x versus e to the b, square root of 1 minus x squared versus square root of 1 minus b squared. This is when you start throwing on your tinfoil hat and say, there's a conspiracy here. There seems to be a connection going on between area and antiderivatives. Now, good news, this time the conspiracy's true. And that's what we're going to build up in the next 2 lectures.